If you've ever watched a production system completely crash under the weight of real-world traffic, you know for a fact that what works perfectly on your local machine almost never survives contact with millions of users. And with modern setups like GraphQL, it's easier than ever to accidentally build a ticking time bomb. Welcome to this explainer. Today, we're putting on our senior engineering hats. We're going to distill the exact architectural strategies that separate junior builders from the senior engineers who actually operate at hyperscale. We'll be diving into the scalability trade-offs, those common but completely fatal engineering mistakes, and the practical, battle-tested backend strategies you need to actually survive in production. Okay, let's just dive straight into this total nightmare scenario. Picture this. It's 2 a.m. Your monitoring tools are telling you the infrastructure is completely healthy. CPU is low, memory is fine, everything looks green. But transactions are failing and the business is bleeding $10,000 a minute. Now, a junior engineer's instinct in this moment is purely reactive, right? They'll restart the pod, clear the cache, and just kind of hope for the best while blaming the code. But a senior engineer, they completely ignore the noise. They aren't looking for a quick fix for the symptom. Instead, they look for the systemic architectural flaw that allowed this failure state to exist in the first place. Because to survive at this level of scale, you really have to shift your mindset from reactive coding to systemic de-escalation. Seriously, at this level, writing more code is rarely the answer. Actually, you can think of every new line of code you write as a liability. It's something that has to be maintained, tested, and eventually debugged when things go wrong. True senior engineering is all about architecting systems that are elegantly simple. It's about removing barriers, not building higher walls. So to map this all out, we're going to break down this playbook into 5 crucial chapters. We'll start with the deletion paradox, then look at surviving the network tax. From there, we'll cure those N+1 query nightmares, especially the ones hiding in your GraphQL resolvers, master caches and idempotency, and finally, tackle zero downtime migrations. Let's kick things off with our first concept, which really builds the foundation of the senior engineering mindset. This is the deletion paradox, and it's all about why creating less actually creates way more value. Notice the stark contrast we have going on here. A junior developer joins a team, builds out these comprehensive new frameworks, adds complex layers of validation, and ships, say, 50,000 lines of code in their first year. And everybody claps, right? But then a senior developer joins that exact same team. And in their very first month, they delete 15,000 lines of code. They might remove an entire unused microservice, kill a redundant dependency, or consolidate overlapping logic. The junior is out there building mountain peaks of code, while the senior carves out valleys. And let me tell you, the company highly values the valley, because less code simply means fewer bugs. And why is this absolutely crucial? Well, think about it. Human working memory can hold about 7 pieces of information at any given time. But a modern backend codebase, that might have 700,000 interacting components. This means every single unused feature, every premature optimization, or just-in-case function directly increases the cognitive load on your team. Senior developers understand that systematically reducing this cognitive load makes the entire engineering org faster, safer, and just infinitely more effective. Moving right along, we need to address a silent killer in modern architecture. Chapter 2 is about surviving the network tax, specifically focusing on protocol efficiency at hyperscale. If you look at this comparison, you'll immediately see why massive companies like Uber transition so much of their internal communications away from traditional REST and over to gRPC. REST over HTTP/111 suffers from a huge bottleneck called head-of-line blocking. Basically, one slow request clogs up the whole connection for everyone else. Plus, it uses text-based JSON, which is super bloated. gRPC, on the other hand, runs on HTTP/2. It efficiently multiplexes multiple streams of binary data over a single connection, all simultaneously. It's a game changer. Just look at the throughput potential here. In rigorous academic benchmarks, gRPC handles roughly 8,700 requests per second. To put that into perspective, that is nearly 2.5 times the capacity of traditional, highly optimized REST setups. When you are operating at massive scale, that level of performance isn't just a fun nice to have. It is literally the difference between your servers staying online or completely melting down during a traffic spike. As this table highlights, the real secret sauce is in the serialization. By dropping a 69-byte plain text JSON payload down to just 20 bytes using binary protobufs, you translate that directly into significantly lower transmission latency.
But maybe more importantly, it massively reduces the CPU cycles required to actually parse that data, so you're saving network bandwidth and heavy compute power at the exact same time. Now, let's move down the stack to the database layer. Chapter 3, Curing N+1 Query Nightmares. This is a fundamental mismatch between code and databases, and it's a massive performance trap, especially in modern GraphQL setups. So, here is the core issue, the dreaded N+1 query problem. Let's say you want to load 100 blog posts, and then fetch the author for each of those posts. Your ORM, or maybe your fancy new GraphQL resolver, fetches the 100 posts in one initial query. Great. But then, as it loops through, it fires off 100 individual, separate queries to fetch each author. You just fired 101 database queries to load a single page. Under load, this behavior will absolutely destroy your backend performance. And the visual difference when you fix it? It's staggering. On the left here, those 10 round trips take about 808 milliseconds. But on the right, if you replace that nasty loop with a single optimized join query, a process known as eager loading, the execution time drops to just 15 milliseconds. Think about that. That is a 54 times performance improvement simply by fixing the way your application communicates with your database. So how do you fix this systemically across a large code base? Senior engineers rely on tools like Data Loader, and this is especially vital in complex GraphQL architectures, which are notoriously bad for triggering deep, nested N+1 problems. Instead of firing off database queries immediately, Data Loader basically hits pause. It waits, collects all the related IDs requested during that execution cycle, and then batches them into one single, highly efficient database call. If you're building a scalable API, utilizing this pattern is pretty much mandatory. All right, moving to Chapter 4, we're going to focus on caching and idempotency mastery. At scale, network retries are constant, and you have to know how to handle them safely without blowing up your memory. But listen, before you blindly add a caching layer to solve all your performance woes, you have to beware of this silent killer, the exploding list. Often, a junior developer will throw data into a static, in-memory list or an unbounded hash map just to cache results quickly. But without a strict eviction policy or a time to live, that list just grows and grows indefinitely. Eventually, it consumes all your available RAM, causing a catastrophic, completely silent, out-of-memory crash. To safely handle these retries and caching layers, you need a bulletproof pattern. Take a look at how Stripe prevents double charging credit cards while processing an insane $640 billion annually. They implement idempotency keys using Redis. Every single request gets a unique UUID. Redis stores it with a strict 24-hour TTL, ensuring memory never explodes, and it also hashes the request parameters. This guarantees that an operation only ever happens exactly once, no matter how many times a frustrated user violently clicks the submit button. Finally, let's talk about deployments in Chapter 5, zero downtime migrations, utilizing the expand contract pattern, because a rollback is not a strategy, it's a last resort. Here's the golden rule. Never, ever perform destructive database changes in a single release. If you drop a column or rename a field in one step, and then the new deployment suddenly fails, what happens? Well, you try to roll back your application code, but that old code is now expecting a column that literally no longer exists in the database. Your database has entered this corrupted zombie state, and you are totally stuck. You absolutely must treat your database schema as a forever forward contract. And this brings us to a brilliant step-by-step technique called the expand contract pattern. You execute this in distinct phases. First, you expand. You add the new column while keeping the old one totally untouched. Next, you deploy application code that migrates by dual writing new data to both places. Then, usually weeks later, once everything is completely stable and backward compatible, you finally contract by safely removing that old schema. This guarantees that at any given point in time, at least 2 versions of your code are perfectly compatible with the database. Zero downtime rolling updates achieved. Now, senior DevOps engineers don't just sit around and hope this happens. They enforce it with strict guardrails hard-coded right into their CI/CD pipelines. They will automatically block any migration that locks the table for more than a single second. They force a strict separation between schema structure changes and heavy data backfills. This ensures that large-scale updates never block application traffic or cause nasty database deadlocks during a critical release. And honestly, all of this brings us right back to our opening nightmare scenario. The dashboards are green, but the business is failing. When your infrastructure returns a perfect HTTP 200 OK status, but the end user is staring at a completely blank screen or an empty shopping cart, you're experiencing what's called a semantic logic failure. The pipes are technically working fine, but they are delivering completely wrong or empty data. You see, the junior engineer monitors the plumbing. They look at CPU, memory, and HTTP success rates. But the senior engineer, they monitor the water quality. You solve these semantic failures by implementing business layer metrics. You start tracking real-world things like average items per cart or search click-through rate. That way, even if the servers are perfectly happy, if the cart volume suddenly drops to zero, alarms fire instantly, because the business logic is what's actually broken. So, what does this all mean for you? This explainer has just walked you through the senior playbook. We've gone from the power of deleting code to mastering backend protocols, conquering those nasty GraphQL N+1 queries, enforcing strict idempotency, and achieving true zero downtime migrations. But the real question is this. The next time the logs are empty, the dashboards are green, and the system turns against you, are you ready to stop just building applications and start engineering them for survival? Take these concepts, apply them to your own stack, and watch your backend systems become truly unbreakable. Thanks for joining me, and keep building.